The concepts of the cyber kill chain, the MITRE ATT&CK framework, and the penetration testing execution standard tests are foundational to understanding cybersecurity operations, threat analysis, and penetration testing methodologies. Each of these frameworks offers a unique perspective on how to approach security from both offensive and defensive standpoints. Let's delve into each of these frameworks and explore their differences and use cases. Cyber kill chain. Developed by Lockheed Martin, the Cyber Kill Chain framework is a part of the intelligence-driven defense model for identification and prevention of cyber intrusions. This framework outlines the stages of a cyber attack from the early reconnaissance stages to the execution of the objective. The cyber kill chain is divided into the following 7 stages. Reconnaissance. The attacker gathers information on the target. Weaponization. Creation of malware designed to exploit the target. Delivery. Transmission of the weapon to the target, e.g., email attachments, websites. Exploitation. The weapon's code triggers on the target system. Installation. The weapon installs a backdoor on the target system. Command and Control C2. The attacker takes control over the target system. Actions on objectives. The attacker achieves their goals, e.g., data exfiltration, destruction. Use cases. The cyber kill chain is particularly useful for threat intelligence and incident response teams to understand and mitigate attacks. MITRE ATT&CK framework. The MITRE ATT&CK adversarial tactics, techniques, and common knowledge framework is a globally accessible knowledge base of adversary tactics and techniques based on real-world observations. Unlike the linear model of the cyber kill chain, ATT&CK is a matrix that includes the following tactics, which represent different phases of an attack lifecycle, along with a comprehensive list of techniques and sub-techniques for each tactic. Initial access, execution, persistence, privilege escalation, defense evasion, credential access, discovery, lateral movement, collection, command and control, exfiltration, impact. Use cases. ATT&CK is used for red teaming, threat hunting, security assessment, and improving defensive strategies by mapping tactics and techniques to known threat actor profiles. Penetration testing execution standard tests. TEST provides a standard guideline for performing penetration tests. It's structured to ensure that the test covers all aspects of a security assessment, providing a thorough evaluation of an organization's security posture. The test framework is divided into 7 main sections. Pre-engagement interactions, defining the scope and goals of the test. Intelligence gathering, collecting information about the target. Threat modeling, identifying potential threats and vulnerabilities. Vulnerability analysis, identifying specific vulnerabilities in the system. Exploitation, attempting to exploit identified vulnerabilities. Post-exploitation, determining the value of the compromised system. Reporting, documenting and presenting findings to the client. Use cases. TEST is primarily used by penetration testers to conduct structured and comprehensive security assessments of an organization's infrastructure. Differences in use cases. Scope and focus. The cyber kill chain focuses on understanding and preventing cyber attacks by outlining the steps attackers take. MITRE ATT&CK provides a more detailed and technique-focused approach that can be used to model threats and improve defenses across various stages of an attack. TEST is specifically designed for conducting penetration tests, covering everything from pre-engagement to reporting. Application. The cyber kill chain is often applied in threat intelligence and incident response to understand and mitigate attacks. MITRE ATT&CK is used across multiple security disciplines including, but not limited to red teaming, threat hunting, and security posture assessment. TEST is tailored for penetration testers and security consultants to systematically assess an organization's defenses. Detail level. MITRE ATT&CK offers a more granular view of adversary behaviors than the cyber kill chain, making it better suited for in-depth threat analysis and defensive strategy development. TEST, while detailed in its execution steps, is more procedural and aimed at testing rather than analysis or defense strategy formulation. In summary, while there is some overlap in their applications, each framework has distinct strengths and is tailored to specific aspects of cybersecurity operations, from understanding and preventing attacks cyber kill chain to modeling and defending against the MITRE ATT&CK to actively testing defenses tests. To theorize an automated penetration testing system utilizing Node.js, Angular, and Cosmos DB, and incorporating AI and machine learning for anomaly detection, we can envision a platform that integrates the principles of the cyber kill chain, MITRE ATT&CK framework, and TEST to guide its operation. This system would aim to automate the process of identifying vulnerabilities, simulating attacks, and learning from each engagement to improve its future performance. Here's a high-level overview of how such a system could be architected and function. System components. Front-end Angular provides a user interface for configuring tests, viewing reports, and managing system settings. It allows users to define the scope of penetration tests, select specific tests or attack simulations based on the MITRE ATT&CK framework, and review outcomes. Backend Node.js handles API requests, manages the workflow of penetration tests, orchestrates the interaction with the Cosmos DB, and integrates AML models. It serves as the central nervous system of the platform, coordinating between the front-end, database, and core testing engines. Database Cosmos DB stores data related to vulnerabilities, attack patterns, test results, and system configurations. Cosmos DB's globally distributed, multi-model database service makes it suitable for this application due to its scalability, low latency, and ability to manage large volumes of data across different regions. AML Engine analyzes penetration test results, identifies patterns or anomalies in data, and suggests improvements or new tests. This component learns from each test iteration, enhancing its ability to predict vulnerabilities and adapt to evolving threats. Operational workflow. Pre-engagement and configuration. Users specify the target system's parameters and select desired tests through the Angular front end. This phase might also involve automated reconnaissance using AI to gather additional target information from open sources. Automated penetration testing. Utilizing the test framework as a guideline, the system automatically executes a series of penetration tests against the target system. These tests are dynamically chosen based on the target system's profile and past attack patterns stored in Cosmos DB. The Node.js backend manages the execution flow, invoking specific scripts or tools necessary for each test phase. Anomaly detection and learning. As tests are performed, the AML engine processes the outcomes, looking for anomalies or patterns in the results that deviate from expected behaviors. This is where integration with the MITRE ATT&CK framework becomes crucial, as the engine can map findings against known attack techniques and tactics, identifying potential new vulnerabilities or methods of exploitation. Adaptation and evolution. Based on the AML engine's analysis, the system updates its testing strategies and methodologies, refining its approach to discover vulnerabilities more effectively. This continuous learning process is critical for adapting to new threats and technologies. Reporting and mitigation. After tests are completed, the system generates detailed reports available through the Angular front end. These reports include identified vulnerabilities, evidence of how they were exploited, and recommendations for mitigation. The AML engine also provides insights into potential security trends and suggests areas for further testing. Considerations. Security and ethics. Implementing such a system requires careful consideration of legal and ethical implications, ensuring that penetration tests are conducted within the bounds of consent and law. Complexity and accuracy. The effectiveness of AML in identifying vulnerabilities and anomalies will depend on the quality and quantity of data available for training, as well as the complexity of the target systems. Continuous improvement. The system must be designed to continuously update its knowledge base and testing methodologies to keep pace with evolving cyber threats. By leveraging Node.js for its scalable backend, Angular for a responsive front end, and Cosmos DB for handling diverse data at scale, this system could effectively automate penetration testing processes. Incorporating AI and machine learning enables it to adapt and improve over time, providing a powerful tool for identifying and mitigating vulnerabilities in an ever-changing cyber landscape. To enhance the previously theorized automated penetration testing system and make it more viable, especially in terms of scalability, security, and observability, integrating the ELK Stack, Istio Service Mesh, and Azure Key Vault alongside other open source tools would significantly improve its capabilities. Here's how these components could be integrated. Enhanced system architecture. ELK Stack for logging and monitoring. Elasticsearch acts as a powerful search and analytics engine to store and query the data generated by penetration tests and system logs. Logstash processes and transforms data from various sources, e.g., penetration test outputs, system logs before sending it to Elasticsearch. Kibana provides a web interface for visualizing Elasticsearch data, enabling easy review of test results, system performance, and security insights. Integrating the ELK stack enables real-time logging and monitoring of the automated penetration testing activities, offering deep insights into system performance and security threats. Istio Service Mesh for microservices communication and security. Istio provides a secure way to manage communications between the services in our system, with features like automatic encryption of data in transit, fine-grained access control, and service-level authentication and authorization. It also offers observability through detailed metrics, logs, and traces, enabling enhanced monitoring of the penetration testing processes and the overall health of the system. Istio's capabilities can ensure that our automated testing system is scalable, resilient, and secure, especially when dealing with complex microservices architectures. Azure Key Vault for secrets management. Azure Key Vault is used to securely store and manage sensitive information, such as API keys, passwords, and certificates required by the testing platform. Integrating Azure Key Vault ensures that all sensitive data used by the system is protected and accessed securely, adhering to best practices in secrets management. By leveraging Azure Key Vault, we can enhance the security posture of the system by ensuring that cryptographic keys and sensitive data are stored securely and access is tightly controlled. Additional integrations. To further enhance the system, consider integrating the following open source tools. Grafana, for advanced visualization of the data stored in Elasticsearch, complementing Kibana by offering additional dashboarding and alerting capabilities. Prometheus, for monitoring and alerting on the infrastructure and applications, which can be integrated alongside Istio for detailed metrics collection. Terraform or Ansible, for infrastructure as code IAC to automate the deployment, scaling, and management of the infrastructure components used by the penetration testing system. GitLab Sift or Jenkins, for continuous integration and continuous delivery, automating the deployment of updates to the penetration testing platform and its components. Considerations for an open source ecosystem. Community support. Leveraging widely supported open source tools ensures access to extensive documentation, community support, and regular updates. Compliance and security. Even when using open source tools, it's crucial to adhere to security best practices and compliance standards, especially when handling sensitive data and performing security testing. Customization and scalability. The open source nature of these tools allows for customization to fit specific requirements and scalability to handle growing testing demands. Integrating these components into the automated penetration testing system not only enhances its capabilities in terms of security, observability, and scalability, but also ensures that it remains a viable and cutting-edge solution by leveraging the strengths of both cloud services and open source technologies. Creating a directory structure for the theorized automated penetration testing system. Integrating ELK Stack, Istio, Azure Key Vault, and other components requires a thoughtful approach to organize the various elements of the system. Below is a suggested directory structure that reflects the system's modular design, separating concerns for clarity and maintainability. Additional objects files, configuration settings, scripts that would be needed are also highlighted. Automated Pentest system. Front-end hash Angular front-end interface. SRC hash source files for the Angular application. Dist hash compiled application ready for deployment. Backend hash Node.js backend API. Controllers hash controller files to handle API requests. Services hash services for business logic. Models hash data models, e.g. for MongoDB or SQLize ORM. AIML hash AML engine for anomaly detection and learning. Models hash machine learning models. Data hash datasets for training and testing. Infrahash infrastructure is code and configuration. Terraform hash Terraform configurations for cloud resources. Ansible hash Ansible playbooks for automation. ELK Stack hash ELK Stack configurations and scripts. Elasticsearch hash Elasticsearch configurations. Logstash hash Logstash pipeline configurations. Istio hash Istio service mesh configurations. Security hash security configurations and keys. Azure Key Vault hash scripts and configurations for Azure Key Vault. GitLab SciHash GitLab Sift configuration files. Required objects and configurations. Front-end. Angular components, services, and modules for the UI. Environment configuration files for pointing to the backend API and other services. Backend. Node.js express routes, middleware for authentication and authorization. Database connection settings and model definitions. AML engine AIML. Pre-trained models or scripts for training models on new data. Data preprocessing and feature extraction scripts. Infra. Terraform files for provisioning cloud resources, e.g. VMS network settings. Kubernetes manifest for container orchestration and deployment. ELK Stack. Elasticsearch cluster configuration for scaling and security, Logstash pipelines for processing and ingesting data from various sources, Kibana dashboard configurations for monitoring and visualization, Istio, configuration files for setting up the service mesh, including gateways, virtual services, and policies for security and traffic management, security, scripts for integrating with Azure Key Vault for secret management, certificate management scripts and configurations for TLS-SSL, 6 configuration files for 6 pipelines, including stages for build, test, deploy, and monitor. Integration settings with GitLab Sict or Jenkins, including webhooks for automated testing and deployment. Additional considerations. Documentation directory. It's crucial to include a docs directory containing detailed documentation for the system architecture, setup guides, usage instructions, and API references to ensure maintainability and ease of use. Testing. Include directories for unit and integration tests within relevant modules, e.g., backend tests, frontend tests to ensure the reliability of the system. Version control. Utilize Git for version control with a well-defined branching strategy and commit guidelines to manage development effectively. This structure serves as a foundation, but the system's specific requirements and the development team's preferences may necessitate adjustments. The addition of detailed README files in each directory, explaining the purpose and contents, will further enhance the understandability and maintainability of the system.